Imagine a beautifully simple factory machine. You drop a raw material onto a conveyor belt, it goes inside, and a highly specific finished product pops out the other side. In mathematics, we call a reliable machine exactly like this a function. You give it an input, and it gives you an output. We see processes like this every day. Think of a bakery oven. You put in a lump of dough, and a perfectly baked loaf of bread comes out. The dough is the input, the bread is the output. Your own body follows similar rules. You step outside on a freezing winter day, and your brain automatically tells your muscles to shiver. The cold air is the input, the shivering is the predictable output. To work properly, a mathematical machine must follow one strict, unbreakable rule. For every single item you put in, you must get exactly one predictable result out. No surprises. Before we ever look at a number, we already know how a function behaves. It is a reliable, guaranteed rule for cause and effect. Now, let's swap out our physical raw materials for numbers. We call our starting number a variable, often represented by the letter x. This diagram shows a mathematical instruction set for our machine. The rule says, take whatever number goes in, multiply it by 3, and then add 5. We can list out our results in a table. If we put in a 1, the machine multiplies by 3 and adds 5, giving us an 8. If we feed it a 2, it gives us an 11. We mark that list of pairs as dots on a flat grid, revealing a clear visual path. This graph shows all those individual dots connected together by a straight blue line. Every single point on that line represents an input and an output following our exact rule. The written rule, the list of numbers, and the straight line on the graph all tell the exact same story. They are simply different ways to document our machine at work. You might be wondering how this differs from an equation. An equation simply states that two things are equal, like a perfectly balanced scale. It describes a static state of balance. A function is active. By isolating our starting variable, we transform that static balance into a step-by-step instruction manual to generate a specific outcome. But what if our machine breaks? Imagine feeding it a single block, and instead of a predictable result, it chaotically spits out two completely different items at random. You wouldn't trust it. In math, if you start with one specific number and your rule gives you two different answers for that same input, the rule is broken. We can audit a graph for broken rules using a tool called the vertical line test. If you slice straight down through a shape and hit two separate points, a single starting number has produced two different results. Perfect predictability is the defining trait. If a relationship has multiple answers for a single input, it is a perfectly valid equation, but it fails the test to be a function. Because a function is perfectly reliable, we can often run the machine backward. If we know the final output, we can reverse the steps to find our starting material. This diagram shows what we call an inverse function, which simply undoes the original work. Our first rule multiplied by 3 and added 5. The inverse subtracts 5, then divides by 3. If our original machine took a 4 and turned it into a 17, we can take that 17, subtract 5 to get 12, divide by 3, and get our starting 4 right back. This chart maps out both of those rules. The blue line is our original function, and the red line is our inverse. Because they perfectly undo each other, they create a mirrored reflection across the diagonal dashed line. Beyond running in reverse, we can also link different machines together in a sequence. You drop a raw potato into a slicer, and then those fresh slices fall directly into a fryer. Taking the result of one math rule and feeding it directly as the starting number for a second rule is called a composite function. Functions give us a reliable, reversible, and linkable set of rules. They let us track exactly how quantities change, step by predictable step.